live ආව.
පාගල යන්නේ 80ට යන්නේ පුතේ. 80ට යන්නේ. අයි පාගල යන්නේ 60ට 60. 60ට 60 නෙමෙයි 80ට 80. හිමින් යන්න බෑ ඉතින්.
ඉතින් පරක් කරන්න ලොකු අවුලක් නෑ. ලෙක්චර් එකක් තියෙනවා. නයිට් රයිඩ් නෙමෙයි ඩේ රයිඩ්.
ඔයා මාමස් වෙන්නගෙන ඉන්නේ ඈනු මොකද ඇරියා. මම හිතුවා ඔය ඉන්නේ වෙන්නේ
නෑ මම අපිට දෙන්න
දැන් මොකද ඔය ඔක්කොම කට්ටිය ලංකාවේ නිදා ගන්න තෝ කරන්නේ?
ලංකාවට
දැන් කැරියෝකේ මොකෙන්ද හැදුවේ කියලා අහන්න. කැරියෝකේ
අන්න මහන කැරියෝකේ මොකෙන්ද හැදුවේ යට
සින්දු හදාගන්න.
ඔව්. හිමනේ දෙහිමියා. හිමුණන් මේ පාර ඇතින් කර. අම්මෝ හෙල්ලෙනවා. පාඩම් කරනවා. පාඩම් කරනවා.
මොකද?
නෑ ඔයා වෙන ඉදියන් නැත්තේ කියලා.
පාඩම් කරනවා. නෑ මං ඔව්. ඒ කියන්නේ ඔක්කොම කට්ටිය පාඩම් කරනවා.
ඔව්.
මොකටද එක්සෑම්?
නින්ද යන්නේ නෑනේ.
දැන් නැත්තම් නිදි පෙත්තක් ගන්න ඕනේ.
නැන්දට කියන්නේ මම බොරු. එයා දන්නවනේ.
මොකද?
ඒයි තාක්. නෑ බොරුවට කිව්වේ පාඩම් කරනවා.
මම දන්නවනේ.
අම්මා දෙක එකක් කරන්නේ. ඔයාලට ලයිව් දාන්න කිව්වේ නැවත කියන්නේ
නැවතත් කියනවා
ඒක. උදේ පහට වෙයිද? ඇයි මොකද්ද දිනවල නැවත?
මම බහුලක් නෑ. ඉතින් ඒක නිකන් අපි යූස් කරන්නේ ආය ආවා කියලා කියන්නේ කතා කරනවා.
ඔව් ඉතින්
ඒක නැවත ආවා.
නෑ ඒක දාන්න. ඒක මන් දන්නවා මම ඒක විහිදුවට තමයි කිව්වේ. රැග් අයියෝ මට පෙන්නලා නෑනේ රැග් කියලා.
මොකෙන්ද හැදුවේ කියලා අහන්නකෝ මේක.
ඔව්. කැරියෝකේ එක හැදුවේ කියලා දැනගන්න.
ඒක කියන්නේ නැත්නම් ඒක
කියන්න බෑ. AI තාක්ෂණය.
අර දැන් මොකද්ද ඉතින් AI ට කාට කියලාද කරන්නේ?
නෑ ඉතින් යාලේ AI.
අයියාලේ. දෙක්කද දෙන්න හිතෙනවා ඔලුව පැලෙන්න. ඔයාට ඔලුව පැලෙන්න දෙන්න කියලා කිව්වා.
මට නෙවෙයි.
එළියේ ඉන්න මනසෙකුට කිව්වේ ඔළුව පැලෙන්නද?
connection නෑලු. එකයි කට්ටියගේ සත්‍ය නැත්තේ. ලයිසන් ගන්නේ වින්ටර් කිව්වනා. Then how did the connection? Visual DJ.
විෂුවල් DJ කියන එකෙන් නේද?
දැන්
මට ඉතින් software එක සම්දි දීලා ගන්න.
අහලා නෑ මම.
ෆ්‍රීද? අහන්න මේක ෆ්‍රීද කියලා සම්දි දීලා ගන්න ඕනේද කියලා. මේ මොකද අනේ මේකේ ඉඳන් හරවන්නේ? තව පොඩ්ඩක් මගෙන් මං යන්නේ. එයාට ඉතන හරවන්නේ මොන මොඩේද?
Virtual DJ එකකින් හැදුවේ. After Effects, Visual Studios. එකක් කියන්න.
උරු කියන්නේ ඉතින් දැන් තුනක් ගෙවුවා දෙකයි නේද එන්නේ?
ඔව් එකයි.
ඉතින් එතකොට
ඒ නෑ දෙක කට්ටියව හදන්න තියෙක නිසා.
දඩ ගාලා. ඒ උඹ දඩස් ගාලා සින්දුව කරනවා.
Adobe Premium. ගහමු කාටද?
එළියේ ඉන්න මිනිස්සුන්ට. දෙන්නටම දෙන්න වෙච්ච පේනවා නේද? දෙන්නම තියාගෙන යන විදිය පිටිපස්සෙන් යන අයට දෙන්නටම දෙන්න ඕන ඔළුව පැලෙන්න.
චට්ටි කිනෝඩෝ පදමු කියලා.
ඔව්. ඔය පේනවාද මෙතන යන එක්කෙනා මේ බලන්න.
මෙයා තමයි ඊව කැපුවේ.
එයා තමයි එහෙම කැපුවේ. අපිට දාන්නෙත් නෑ. ඉතින් ඔය යනවා. ඔය දැන් අපිට යන එක්කෙනා පාරට බ්ලොක් කරගෙන දෙන්න හිතෙනවා.
Road rage with me. Road rage. Suno AI willing hadan.
මේ නිකන් ඉන්න කියන්නේ නැහැ කියන හතර මට ඕනුනහම මං සිදුව කියවන හදන්නද.
Hello Yakuza.
අපිට දාගන්න.
හුඟක් සීතලද? අද එච්චර සීතල නැහැ. වෙන කීයද 6යිද?
6යි පේන්නේ. එකක් ඇති 12ක් 13ක් ඇති. එයා නම් දැන් පුතේ මෙන්න මේ නෝනත් එක්ක. දෙපැත්තේම වාහන තියලා
ෆෝන් එක ගැන හිටි.
still
ලංකාවේ එක්කෙනෙක්ද කොහෙද කියන්නේ.
ආවෙ කෙනෙක් නෝනා කෙනෙක් යන්නේ.
දිස් දැම්මලු හදපු. දැන් බලන්න බෑ. බැලුවොත් මම හිතන්නේ ස්ට්‍රීම් ලැබ්ස් යනවානේ.
නෑ යාට ඉස්සරහට. ඔයා හරවන්නකෝ.
නිතිෂ් හායි කියනවා යාට.
හලෝ පුතේ.
හායි කියන.
හලෝ පුතේ.
PC කෙනෙක්. අනේ මං එහෙම කරන්නේ. මන්න මේකෙන් යනවා හරිද?
මොන කිය?
ස්පීඩ් මේන්ටේන් කරනවා.
මේන්ටේන් දැන් මේ වැඩේ කියන්නේ මේ තියනවා එහෙම දාලා හැබැයි මේ තිබුණු කැමරා ඔක්කොම අයින් කරලා තියෙන. ඒ හින්දා අපිට
නෑ ඒ කැමරා තිබ්බේ වේගෙන් යනවටනේ. හිමින් යනවා නෙමෙයි.
ස්පීඩ් කැමරා වලට. හැබැයි පොඩි සිග්නල් ගත්තොත් ඉතින් ඉවරයි.
ෆෝන් එකේ ඔයා ගැම්මට යනවා කිව්වා. ඔයා ගැම්මට එනවා කිව්වා.
සුදුට එක ක්ලාස් එකයි නම් ඉතින් දැන් එතකොට 7 වෙනකන් ඉන්නේ කොහොමද ඔයා?
ඇයි ටෙස්ට් එකනේ මට?
ටෙස්ට් එක කීයද?
ඒක පටන් ගන්න 6ට.
මොකද කරනෝනේ? කොපුලානේ හැබැයි ටක් ගාලා කරලා නේද?
හරි.
අප බලන්න ඕනේ.
මොකක්ද කියන්නේ? ඔය ඉතින් මුල් දවස්වලම ඉඳගන්න ගත්ත තාත්තත් එක්ක බය හිතුනේ ඊට පස්සේ ඉතින් නෝනන්න 80 පාඩවල මම මාගෙන් තනි පාඩ නිසා.
අයියන් ඈ.
රෙඩ් උනා.
That's okay.
ලයිට් එකේ රෙඩ් එකේ ගියා.
මම දැක්කේ නෑ.
එහෙම යන්නේ නැහැ ඉතින් පරිස්සම යන්නේ.
පොලිසියෙන් දෙකවල.
නැන්ද සීත නැද්ද කියලා.
සීතලයි මේ හත් දෙක සීතලයි.
මාට්ට. අවයි. බය වෙන්න එපා. අද උදේ කැම්පස් එකේ මාත් දැන් මේ රෙඩ් ලයිට් එකේ මං කිව්වා. එයාත් රෙඩ් ලයිට් එකේ ගියේ කියලා. බය වෙන්න එපා කියලා.
ලයිට් එකේ මිනිස්සු බය වෙන්න වෙන්නේ පුතේ. දඩ ගන්න වෙන්න. කැමරාවට සෙට් වුණොත් තමයි බය වෙන්නේ. දඩ ගන්න එක තමයි බය වෙන්නේ. අයියෝ ඉතින් කොහොමද යන්නේ? උත්තර වේගෙන් ආවත් මේ චූට්ටයි යන්නකෝ ඉස්සරහට. කීයද පියා? 2:25ට වගේ නේ පුතේ.
22කට.
හා?
ඔව්. කැනල් එකට එන්න ඕනේ. නේ.
මේක කියා? මේක තමයි මොකක්ද?
රුපියල් 1000ක් කවුරුත් නැහැ.
රුපියල් 1000 ලංකාවේ. මේ මෙහි ඩොලර් 300ක්. 300ක් කියන 300 මට මතකයි. 300 ගානක් ආදායම
හෙලෝ. ඔටෝ ඩිටෙක්ටර් එක නැත්තම් බැලුවොත් ඔව් ඔටෝ වදිනවා. මේ ඉස්සර අර අම්මා කිව්වාගේ ස්පීඩ් කැමරා තිබ්බා. ඒ කියන්නේ අර ස්කෝල් වල ගාව වගේ තමයි මේ එතන 40ට යන්න ඕනේ. ඊට වඩා ගියොත් කැමරා වදිනවා. ඒකේ පින්තූරයක් වදිනවා. ඊට පස්සේ ඉතින් දඩ තමයි. හෙලෝ ඉන්නවා. ඔව් ආයා. ඔව් ඒකනේ.
කොතන යන්න? කීයද ක්ලාස් එක පටන් ගන්නවද?
2:35ට.
2:35 විනාඩි 10ට 50ක්.
එතෙට යන්නත් ඕනේ.
එතකොට කියලා දාන්න වහන්න. වැඩි කොතනද රහින්නේ කියන්නේ?
අර මේ
කන්නම් මේ. එතන මෙතන.
විශාල යන්න.
මොකද එක්සෑම් එක කරන්න පුතේ?
හරි.
විශාලයි. මොන එකක්ද දෙන්නේ නේද?
හරි. විශාල. හිතාගන්න ගේට. දුවම කමන්නේ අනි කොහොමද පරක් වෙයිද? දැන් නම් කනෙක්ෂන් අවුල් වෙන්න පුළුවන් ටනල් එකේ යන්නේ.
I got a practice test from a friend
Oh
in
nice.
the class, and they're using the stuff from this lecture in their tests. So
Oh the
they just had
okay. Wait, could you send me that?
So that's what I think I finished more or less around here last class. So if you have two vectors, then they will be equal when they have the same length. They of course have the same one part, but they need to have the same number of rows. Yeah, the same size. And in addition to that, you must have the same element position by position. The first elements must be equal, the second element must be equal, and that will make the vectors to be equal. And of course, if you have three elements, it's the same. X1 equal to X2, Y1 equal to Y2, Z1 equal to Z2. If you have 4, T sub 1 equal to T sub 2. If you have 5, always position by position.
Okay, I understand.
That is exactly the definition of equality of matrices. When two matrices were equal, when they have the same dimension and they were position by position with the same number. These are matrices, but they are matrices with one column. So it's exactly the definition in the case of one column. You need to have the same size and you need to be equal position by position. Whereas 2 or 3 or any number that you have. So let's suppose that I have two vectors U and B. The same are 3, but you can do it for R2 by removing the third component there. What happens when we sum them? When we sum them, in terms of my matrices, we already defined the sum of two matrices, right? The sum of two matrices, these are one column matrices, they need to have the same dimension. They have one column both. They need to have the same number of rows, meaning you cannot sum an element from R2 with an element from R3. Because there are two guys and then we have 3. You need to have the same dimension when you sum matrices. So they will need to be on the same place, either both in R3 or both in R2 or both in R4 or wherever you want. But then what is the sum? It's just the sum position by position. This is the definition of summation of matrices. Right? So it is x1 plus y1, etc. What is the product of a vector times a number, a scalar? Well, if you have a matrix and you multiply by a scalar, what it does, the scalar multiplies everywhere, right? So you need to multiply the scalar everywhere. Rx1, Rx2, Rx3. If you want to do the subtraction, what is the subtraction? The addition, but the second one is the opposite. You need to change the signs on the second one, right? So in other words, it is x1 minus y1, x2 minus y2. So you can do operations with matrices that are doing the operations here in R2, in R3, and so on. So, for example, if I have 1, 4, 9 in R3, this can be and another one, let's say 0, minus 1, 2, also in R3, the same place, the elements. So I can sum them, and that would be the sum like this, right? 1, 4, 9 plus 0, minus 1, and 2. So that is solve this 1, 3, 11. This is how we have been doing it so far. But now we have the other notation too. So in the other notation, you are solving like this. 1, 4, 9 plus 0, minus 1, 2. And what is equal? You need to sum position by position. So it will be 1 plus 0, 1, 4 plus minus 1, 3, 9 plus 2, 11, and of course it's the same result. Okay? So when you sum those vectors, you can either sum it as we have been doing it for matrices, just one column matrix, or you can do it position by position with the triple, or the pair, or whatever number you have. They need to have the same size. You cannot sum a guy that has 3 with a guy that has 4. That's not defined. But it's in the matrix, it's not defined either. Remember, you cannot sum two matrices if they have different dimensions. Now, I would like to leave for you to think, what are these things doing? So this will end up being an exercise at some point. This is hard. So if you have a vector, let's say I have a vector here, u, some numbers, 2, 4, 5, I don't know, whatever. Okay? Let me do it in R2 first, or in R2 directly, because it's easier to see what I'm doing. 2, 4. I have a vector in R2, 2, 4. And I will multiply by a scalar. Let's say my scalar, and real number, is 3. Okay? So if you do 3u, what do you obtain? 3 multiplies every place, right? It's a matrix. So I give you 3 times 2, 6, 3 times 4, 12. Okay? Now draw those two elements of R2 with your x is 1. So 2, 4, say 2, 4, 2, 4. Let's say it's here. This is 4, this is 2. And I should have chosen a better number, but anyway, you can do a drawing better than me. And what is 6 times 12? Sorry, what did I say? 2, 4, not 4, 2. So let me change this. This is 2, this is 4, this is 6. This is 2, this is 4. This is 6. This is 8. This is 10. And this is 12, let's say. So 2, 4 is right here. This is 2, and this is 4, right? And 6, 12 is somewhere here. Right? So this is, when you consider as a vector, is this vector here, right? And this other one, it has the same direction, but somehow is longer. How much longer? Exactly 3 times. Because what is 3 times 2, 4? It's 2, 4 plus 2, 4 plus 2, 4. So you sum it 3 times the same vector when you multiply by 3. So what the scalar multiplication is doing to the vector is sort of expanding the vector, making it larger in the same direction. It's not changing the direction, it's just pushing it to be longer. How much longer? A scalar times, 3 times longer in this example. What happens if I do 1/2? If I multiply by 1/2? If I multiply by 1/2 u, I get 1, 2, right? So it sort of went here, 1, 2. It went exactly, was cut half. So basically, this is scalar multiplication. You check it here on the drawing on the plane. What it's doing is either enlarging the vector, doesn't change the direction, just pushing it longer. How much longer? Well, if your number is positive, it will be longer. It will be 3 times, 2 times, whatever the multiple you have. But if your number is a multiplication is smaller than 1, it will contract it. It will get it smaller. It's still in the same direction. So scalar multiplication, the only thing that really is doing, the scalar multiplication is defined, before. We have this definition of multiply the element by every place in the matrix, right? But what it's really doing, in terms of here, is pushing the point to be either longer, if the scalar is bigger than 1, how much longer exactly the scalar that you are multiplying? 3 times if you multiply by 3, 4 times if you multiply by 4. Or smaller, you can multiply the smaller number. The exercise then, I think because I already explained the scalar multiplication, so 2 these for addition. So, take 2 guys, take U, let's say 2, 4, 3, 4. Take B, 1, 1. What is U plus B? In the plane. You have U, you have B. Where is going U plus B? Add the places, right? So you have 2, 4, draw 2, 4. 1, 1, draw 1, 1. And see who is the summation. Of course, the summation is 2 plus 1 plus and 4 plus 1, so it's 3, 5, right? So this guy, 2, 4, I don't want to continue. I will be end up doing everything here. But this is a 2, 2. Grab the 1, 1 and see where is going this 3, 5. So there is a geometric interpretation here of this multiplication. I already played the multiplication. It's not changing the direction. It's either pulling it longer or smaller. Right? If you multiply by 1, you keep it the same. You don't move it. Yeah. The sum is also has some geometric thing. So play a bit with that. Okay? And of course, the definition for R3 are the same for R2. The only difference is that, remember, you cannot sum a guy that has 2 guys with a guy that has 3 guys. That's the very first class of matrices. You cannot sum 2 matrices if they have different dimensions. Here they will have 1 column, but the number of rows depends on if they're in R2, in R3, or in R4, or R5. Okay. So, okay. So now here are some basic operations that you can do with these vectors. Let's say in R2, but of course this is the same with R3. Again, the important thing is if you are summing R2, all must be in R2. If you are summing in R3, all the vectors must be in R3. The scalar is just a number in any. But here are some operations that will come up a few times today. So I can do associativity. Associativity, remember, is you can put the parentheses in any order you want. You can do whoever you want first. That's no problem. Moreover, it's no problem commutativity, and at this point, you need to remember that this is addition. I'm not talking about multiplication of the elements, I'm talking about addition of the elements. And if you go back in the matrices, there was no issue, no problem if you sum this way or that way. Because in the end, you are summing real numbers inside, so it will not really matter the order. So you have associativity of the addition, you have commutativity, you have more. You have a 0 guy. It's a 0 vector that when you sum your u plus 0 for any u will give you u. 0 is the identity, right? We call the identity, additive identity. It's the guy that when you sum it, doesn't change anything. And you have the opposite for the negative. So if you give me any vector, there is another one that when you sum it will be 0. Put a vector, change the sign. So if you give me here 3, 4, there is a vector here that I can sum, and it will give me 0. And that vector is, if I have a 3, I put a minus 3. If I have a 4, I put a minus 4. So there exists, for any vector you give me, there is another one that it can sum to 0. And 0 was that previous one, the identity one. Okay, that's for additions. But I also talk about multiplication by scalars. So what happens when you multiply by scalars? Well, if you multiply the number 3 times the sum of 2 vectors u plus v is the same as doing 3u plus 3v. You can check it with numbers. It's very easy to check. You can also have a summation of scalars multiplied by one single vector that again decomposes r times u plus s times u. You can also multiply u times a number s and then by a number r, but that's the same as multiplying directly by the product of the numbers r times s. And last one, there exists a real number called number 1, that when you multiply 1 times any vector, give you the vector. Because 1 multiplied by any value will give the value. These properties that these vectors in R2 and R3 have, I will tell you some means that the Rn will have. There will be no difference if you are doing 4, 5, whatever you want to do. But moreover, there will be the basis for the definition, well, one of the most important definitions of the course, that is the definition of vector space that is coming soon today. So, okay? Now, there is one thing missing here, and is the length. How do we compute the length? Yeah, this seems to be an important notion in all this business. So let's go back to the case 2 by 2. So I have a case 2 by 2 here. So let's suppose that I have a point here. Yeah, that's marked. This point here. So this point here has some x value and has some y value here, right? And I want to measure this length, the length of this vector. If you remember from your high school, this is a 90 degrees, right? So this is the hypotenuse of the triangle, and these are the two sides of the triangle. And there was a great guy of Pythagoras that 2,400 years ago realized how to do that measure, because he realized that the square of this length is the sum of the square of those lengths. Now, what are those lengths? If my value here is, I don't know, let's say 3, 4, saying something. So what is this size here? It's exactly this size here. So that means that my length square is the sum of 4 squared plus p squared. So 4 squared plus p squared is the length that I want. Square. That's it out. Okay. So what's the length? The square root of this. And that is the definition for an exam, right? So it's good to x and y. Let's call it x1, x2, x3. So if you have 3 there and 4 there, then your length is the square root of the sum of the squares, 3 squared squares. And this is the definition of the length of a vector. It's also called the norm of a vector, the magnitude of a vector, and it has a few other names. It's just a number. But it's an important number. It tells you how long the vector is. And you can do it for 3 or for any number you want. So if you are working in R3, the length is defined as, or the norm is defined as the square root of the sum of the squares. So this is the magnitude, the length of the vector, things like this. Okay? So if I have this vector here, minus 3 and 1, what happened with the norm of this vector? Square root of minus 3 squared plus 1 squared, square root of 10. And if you have 3 guys, 4, 1, and minus 2, well, the square root of 4 squared, 1 squared, minus 2 squared. And so it's very easy to compute those lengths. Another thing important, not for today, but it will be important for the next test and exam, you don't need to compute this sum. You just give a square root of 10. You don't apply the computer and tell me 3 dot whatever. I don't want to see that. Square root of 10 is perfectly fine with me. Okay? No need to use calculator. And I will not use calculator here. I will just leave it as a square root of 10, square root of 21, whatever it is. Okay? So, another thing that we will not need for a while, but we will need later, and when I talk about later, I'm talking about 1 week before the end of the class, more or less. So we are talking about week 11 of the course. We are in week 5. So it is the notion of unit vector. So what is a unit vector? Nothing else than the vector that can length. Okay, very simple. But the issue here is we will be caring about those. We will be wanting to have unit vectors, okay, in something called Gram-Schmidt, and orthogonalization is one of the very last topics we will see in front. So how do we get a unit vector? Very simple. You compute the norm, and then get the vector and divide by this number. Divide, yeah? Do the proportional way by cutting this, dividing by the norm. And that will produce a unit vector. There's only one catch. The vector cannot be 0. Whether it is here, B is any non-zero vector. Cannot be 0. Why cannot be 0? Because let's suppose that your vector is 6. Who's the 0 vector? Like this, right? Let's say it has 3 values. What is the norm of this vector? The root of 0 squared plus 0 squared plus 0 squared equal? The norm of that guy is 0. And you cannot divide by a number 0. This is not mathematics. That goes in somewhere else, going to infinite. It has something else to do, nothing to do with this course anyway. So you cannot do it if the vector is 0, because you cannot divide by 0. But other than that, for any other vector, you divide by the norm, and that will give you a unit vector. So for example, you grab a vector like this, 1 minus 2 and 3, and then you do the squares. Observe what happens when you do the square, right? What happens with those negative signs? You see that will never matter, right? It's like having the positive here. You see, this, you will do the square, and a minus a square will be positive, right? So you are summing positive values here. The only possibility that are zeros there will be the 0 vector, but you exclude it, so that's fine. That doesn't happen. So those values here will be some positive quantities, and this will be the square root of a positive quantity. Like for example, 14 in this example. Yeah, the negative values don't matter, negative or positive. Yeah, they have no influence, the negatives, because they are put in square. Those are positives. So now you get this square root of 14, and you divide by square root of 14, and of course gets ugly. You get 1 divided by the square root of 14, minus 2 divided by the square root of 14, 3 divided by the square root of 14. But if you compute the norm of this one, if you compute the square root of the squares of this one, it will be 1. Basically, the numerator will produce an square root of 14, and the denominators have a square root of 14, and that will end up being 1. As I said, for us, right now is why I care. Yeah, sure. But we will care. Okay? You just wait. I'll come back to this very late in the course. So, what is the operation to get a vector, to get a unit vector? Divide by its norm. That's it. Okay? You can check it, do the computations here. Compute, square this one, square this one, square this one, inside the array, square root, and you will see that you get 1. All right? So, any questions? Because what I told you for R2 and R3, everything, now I will tell you I can do it for 4 or 5 or 6, or any number for you. So, any questions so far? All right. Then we move on to the next set of slides.
I feel like there's so many of these to memorize. Like I'm gonna get them
And
fast.
as I said, this will end up introducing a very important notion of vector spaces and subspaces. So, the first thing we will talk about will be vectors in Rn, and then I will talk about vector spaces and subspaces. Vector spaces will end up being one very fundamental and important concept, and in this course, it's one of the most important notions of the course, actually. It turns out that if you have a vector space, then you can have something called basis for the vector space. And a basis will allow you to compute any vector in the space, let's say you have, for example, R3. You will only need 3 vectors, 3 only, to represent any point in R3. How will be represented? As a combination of the 3. What combination? Well, this course is linear algebra, so the combination is a linear combination. You can sum them, you can multiply by a scalar, or you can do equations multiplying by a scalar and adding. And that's all that you are allowed to do. And with that, you can represent any element in the space. So the notion of basis is quite important because with 3 vectors, I can represent any vector in R3 that of course are infinitely many. But I only need 3. And 3 vectors, 3 poles, 3 elements in like this. 3 of course, 1, 0, 1, 1, 1, 0, 0, I don't know. They will need to be special because they will need to satisfy the notions of spanning sets and linearly independent. These 2 notions will be the ones that, when you pass those tests, you are a basis. And everyone is represented with very few values. How many guys? The dimension. So R3 will have 3 because the dimension is 3, and that's the 3 on the top of the R. And R2, we have 2. And so on. So, but this is actually far more general than Rn. So there are other vector spaces, not only Rn. But anyway, so that's what we are going today and next week. Yeah, we will define this object called vector space, and then we will talk about when some subset of it is already a subspace in some route. Okay. And then later we'll produce next week those bases and dimensions and so on. And then we'll come back to matrices as I am pointing them random combinations that will be related to what we do. But first, let's generalize to Rn, what we just said for R2 and R3. Suppose that n is a positive integer. If it's 2 or 3, we already saw it, but you can assume now any other value. Then whose Rn is the set of order n tuples x1, x2, xn, where those guys are real numbers. That is this set. What is the difference with before? Before you either have 2 or 3, now I need to put dots here, because I don't want to say 4, 5, 6, I just want to say any n you want. Just give me any n you want, a positive integer, right? 100. Okay. What is R to 100? Is one tuples of 100 elements, or 100 element tuples, where each of the elements are real numbers. And guess what? We will be summing them and multiplying by scalar just like we did for 2. So there are 2 ways to denote those elements in Rn. Either you do it by enumerating like this, by commas, like sort of in a row if you want, but with commas. It's not row of a matrix, it's just an n tuple like this. Or you can use a column matrix. So it has 1 column, but it has n rows, where n is that n that is here. And if you're doing this for an n, you cannot change. If you decide to do 4, then it's R4, you need to have 4 tuples. You cannot have a 4 tuple and a 2 tuple, a 2 tuple, because operations are not defined. They need to have the same size. Okay? And we talk about norms. What is the norm now? Well, I already told you I did x1, x2, x3 because I will do xn. So if you have n guys here, the norm of the vector is simply square root of the sum of the squares of the n guys there. So for example, if you have a 4 tuple, it's a 4 tuple, there are 4 guys here. It's an element in R4. Then what is the norm? 1 square, square root of 5 square, so on, right? So square root of 1 square, square root of 5 square, minus 2 square, 4 square. Square root of 5 is nice because when you do the square, you basically kill the square root, right? That would be 5 directly. The minus doesn't matter. So you get a 1 plus 5, 6 plus 4, 10 plus 4 plus 16, 26. And of course, you just leave it like that. Don't compute more. Root of 26 is 5. Okay? So it's all the same that we did. All right, so all the same. For example, sum. If you need to sum two vectors in Rn, in the nth dimensional space that we will see when we see dimension and so on, then you just sum it by summing position by position, and you multiply by a scalar by multiplying the scalar on every position. Just like you did for matrices, and you are using it today in the test today, right? Just the same operation for matrices. These matrices are one column. That's the only special thing. All right? So, for example, if I have these two vectors in R4, so just for couples, what is the sum? You need to sum position by position, right? 7 plus 1 minus 2 plus 2, etc. It gives you 8, 0, minus 2, 3. If you need to multiply by 5, of course you multiply by 5, it gives you 35 minus 10, 5. All right? Just the same. It's kind of, you cannot see it like in a plane or in a space, but still mathematically or numerically or abstract way, whatever, it is the same. So let's go back to those operations. Remember that we saw that in the case of R2 or R3, I don't remember, there were 4 operations that you can do with sum of vectors and 4 operations that you could do with multiplication by scalar, right? Well, here we will have those same 8 operations, but we will have 2 new operations coming. And here is the first one. If I sum 2 vectors in Rn, the result must be a vector in Rn. This is called that the Rn is closed under vector addition. So if you sum 2 intuples, the result, and these are real numbers, you need to have a real number intuple as a result. Here makes not much sense because it's obviously true, but as you will see soon, when we talk about subspaces, some will have this property and some will not. So it's something that it will be important for the subspace. You see vector spaces and subspaces? For the subspace part, it will be quite important. The others are as you have seen. X plus y is y plus x. X plus y plus z, to the parentheses wherever you want. There is a 0. X plus 0 is 0 plus x. There is a minus x. X plus minus x is 0. Right? Now, scalar multiplication. If you multiply a scalar c by a vector x, you need to be again in Rn. This is new. Number 6 and number 1 are new ones. They are requiring that when you add 2 guys, they might stay in the place. And when you multiply by a scalar, you must still be in the place. As I said, for Rn are clear, but I will show you examples that will not satisfy that when we talk about subspaces. And the rest, c times x plus y, cx plus y, etc. Right? These ones are exactly as before. And these 10 properties are quite crucial because these are the things that will define what is a vector space. Of course, Rn is a vector space, but there are other vectors. So we have those properties. Some final consideration with the scalar multiplication. Those minus really don't really matter, you know. They will not change anything in terms of the length, in terms of the norm, because that is computed by computing a square root of the squares. And those squares, those minus, are like nothing there. So you have this situation that if you multiply a vector by a constant and you compute the norm, that will be the same as the norm of the vector multiplied by the constant, but the positive value, the absolute value. That is to say, if this was negative, it will be the positive value. And if it was positive, it's the same value, right? So for example, if you do minus 4b, you will get the same as 4 outside times the norm of b. And if you do minus b, it will be the same as the absolute value of minus 1, that is plus 1 b, so the norms are the same. So for example, if you have a vector b here, something. course, I have the minus b. Minus 4, minus b. Let's compute the norm of this one. Norm of b. Square root, 4 squared plus 3 squared. 16 plus 9, 25. Square root 5. So that's okay? This one. Norm of minus b equals square root of minus 4 squared plus minus 3 squared. 16 positive plus 9 positive, 25 positive, 5. Same number. Okay. Those minus didn't matter at all because in the squares they disappear. They end up being the same numbers. Okay. So this is for the constant. This minus here. If you want this minus 1 times b, right? But this is saying the first property is actually you can do it for any number you want. The minus 1 came up as a 1, right? The minus 1 came up as a 1. Yeah, 1 times b. Well, if you have a minus 4, it will come up with a 4. So do it as an exercise. Exercise. So for this b there, right? Let's say 4. Minus 4 times b is equal to 4 outside times the norm of b. I just did it for 1. Do it for 4. That's what I'm saying. So this will help you on the norm. The norm computations are rather easy because we don't really care if the square root of any number. We just leave it like that. So the other thing is just computing squares and then adding them inside the square root. Okay. Now, if you don't have any questions, I will go into what I said is one of the most important concepts of the course. That is what is a vector space. We will be talking about how to write elements in a vector space, a lot of things about vector space. So, questions? All right. So for the definition here of vector space, we will forget for a moment about the reals. There are 2 or 3 ahead. All of those are examples of vector spaces, but there are other vector spaces. So let's take a look at the definition in general. So a vector space is a set of elements, set of objects. For example, in R3 are triples like this. In R2 are tuples like this. Also, in matrices we have a matrix, It depends on the object that you have. So it's a set with objects. And in that set you can define 2 operations. And the operations are, surprisingly, addition of 2 elements and multiplication by a scalar. Very important, I'm not saying multiplication of elements. Only multiplication of 1 element times a number, and addition of the objects. You need to have that definitions. We don't care for the definition of vector space of other things. Later, of course, we will care of doing products and so on because it's nice. It will be different from summation, but it's not in the definition of a vector space. And now, a set with those operations, but the operation has to follow some properties. And no surprisingly are the 10 properties that we have seen for the real numbers. They are, first one, if you add 2 elements in this set V of whatever things, you need to obtain, your definition of sum will give you an element in the same set. Okay? So that's close under vector addition. Then, of course, commutativity, associativity, the zero guy, the opposite or inverse, and here the inverse, right? So there's a minus e, that's something we use 0. Those are with respect to the addition. Now we go to multiplication by a scalar. First one, multiplication by a scalar is closed. If you multiply a number by a vector, you are in the same vector set. Your set was vectors or whatever they are, I don't care. But if you multiply by a scalar, you must be inside there. And the rest that you have seen. You multiply the number times the summation. If the number multiplied each one, and the addition of CU plus CU. If you have the addition of the scalars times the vector, is each scalar times the vector added. If you have two numbers and you multiply one first and the other, is the same as multiplying the numbers first, one times the vector. And there is a 1. That is actually the real number 1. This is not the identity matrix. Okay? If I talk about matrices, for example, this will not be the identity matrix. This is the number 1. That one, that's the real number. Okay? So the first property refers to adding the vectors. The last 5 ones are multiplication of the scalar times vector. Okay? And of course, here is your first example, or many examples, R2, R3, R4, R5, Rn, all of them are vector spaces. Why? Because we have defined an operation of addition of vector spaces, addition of vector elements, and multiplication by scalar. A vector times a scalar, an entapole in Rn times a scalar, defined, multiply the scalar every space. And those operations satisfy all those 10 properties, as you can check. We can check them today. So that's good. We do have some examples. They sort of summarize it like this, right? If V is equal to Rn, if your vector space is set here is Rn, then with the operation defined before of addition and scalar multiplication, you give me an entapole like this or like that, doesn't matter, you can write it as a matrix column or this entapole. This important is the order. You 1 is before you 2, so you 1 is on top of you 2. The order is important, right? But nothing else. Then that is a vector space. But of course, here in red, there are many other examples of vector space. This is not the only one. So let's see one. Let's consider matrices. For example, 2 by 2. In reality, it doesn't matter the dimension. It could be n times n, whatever you want to have. So what are these matrices? But it's good to see they fit nicely there. So let's consider 2 by 2 matrices first. And so these are matrices like this, right? They have 4 real numbers, A, B, C, D. And all possible real numbers that you want is a matrix 2 by 2. So you vary A, you vary B, you vary D, you vary D, A, C, and D, and you get all the matrices that are 2 by 2. Well, can I sum them? Yes, I can sum them because 2 of them have the same size. Remember that if they don't have the same size, you cannot sum them. But if they have the same size, you can sum them. And the summation is position by position. So you can do the sum. So that's good. That is close under addition, because if I sum 2 matrices 2 by 2, the result is a matrix 2 by 2. So it's close under addition. And of course, I can do commutativity, because basically inside each position you are adding 2 real numbers. You can add it in any way you want, in each position. Okay. Now who's the zero element, the zero vector in this vector space? It has to be a matrix 2 by 2 because the 0, if you go back, is an element in the vector space. Right? Is it 4, I think? Here you go. There is a 0 vector in V. Here, in V. So my V was a matrix is 2 by 2. It has to be the 0 vector, the 0 matrix 2 by 2. That's no problem. We look at 0, 0, 0, 0. So we look at that way. Okay. So you can check rather easily that this is the vector space. It satisfies all the 10 properties that we have commented. Moreover, does it matter to be 2 by 2? No, it does not. any size you want. It doesn't need to be square. You can pick any size, like matrices 3 by 4, 3 rows, 4 columns. Of course, you will be having two matrices that have 3 rows and 4 columns. The result has 3 rows and 4 columns. Every single operation is done on those matrices, and there is no problem because they have the same thing. Okay? So yeah, actually, those are vector spaces. Matrices form vector spaces. Now, who's the 0 and who's the 1? The 0, I already told you, is the 4 zeros. But here I need a 1. Yes, you need a 1. But this 1 is the scalar one, the scalar one. It's just a real number, 1. This is not a matrix 1. Here, it says 0 in V. So 0 must be a matrix of whatever size you're talking about. But here is scalar, is the number 1. I do not need the identity matrix. Okay? So the identity matrix came up because we're doing product of matrices, remember? The identity was, the matrix, you want the inverse, multiply, will give you the identity matrix. So it's a matrix that requires sort of in product terms. It's actually the identity of the product. You multiply any matrix times the identity, give you back the matrix. But this is not required here, because the one there is not the one of matrix. Why not? Because the only thing you are doing is summing elements and multiplying by a number, not multiplying the elements. So you are not multiplying matrices in vector space. We can define the operation of multiplication, and that's fine, you can do whatever you want. But it's not in the definition of vector spaces. Right? So the vector spaces, again, go back to that linear plane. Remember the very first class? Linear algebra, linear. Yeah? Sums and multiplication by scalars. Okay? So that's what the vector space notion brings. Okay? So this one is. So now I will define a notion where that idea of closure, that the sum must be an element of the set, becomes important. And that is the notion of subspace. So, you know that when you have a set, you can have a subset, right? What was a subset? Well, there were some elements of the original set, but maybe not all. A subset could be the entire set. In general, you are interested on sets, subset that contains something different than the entire set. So we want to have the same notion here. We want to have something that is a piece of the set, of the complete vector space, but maybe not totally. So it's a subspace. And what will make it space? For now, it's a subset, right? It's a subset of V. But to make it a space, a subspace, you need to be on the space in your own right. So in other words, once you consider the operations inside the set S, and only for the set S element, you must satisfy the 10 properties. And which are the important ones? The important ones are, the first one, that if you sum two elements in S, you must be in S. If you are a space, you cannot grab two elements and get away from there. So every time you add two elements, you might still be in the space. And that was the closure for addition. And the multiplication by a scalar. If you get an S and multiply by a scalar, you need to still be in S, because maybe when you multiply by a scalar, you get away from S, and you're in the inside bigger space. The other ones don't really matter much, because let's say I'm doing something for a matrix, and now I'm doing for some subset of the matrix. Still be additions and multiplication, and we have commutativity and associativity, nothing like the other properties really matter. The one that will define the subspace are actually the close, for addition and product. That actually will be a result. But before we go there, let's take an example. So here's an example of a set of matrices. Okay? So consider the matrices 2 by 2. All right? You consider the matrices 2 by 2. They have A, B, C, D. Right? Any real number you want. For the 4 elements of the matrix. For the 4 elements of the matrix, right? But now I will consider a subset of all the matrices. So here is my M 2 times 2. Are basically matrices like this: A, B, C, D, where A, B, C, and D are just real numbers. And I have, of course, 4 of them in the definition of the matrix. And now we will define a subset that I will call W, that will be matrices that have, maybe change the numbers if you want, R, S, T, but then you have a 0. But R, S, T are real numbers. First of all, W is a subset of this. W is a subset. Why? Because every single matrix of this shape is a matrix 2 by 2. Of course, this set contains less elements than this one. For example, the matrix 0, 0, 0, 1 is in M22, but this matrix, this is the same, 0, 0, 1, is not in W. So this set W is properly contained in the matrix. Every single matrix of W is in M22, but M22 has more stuff. Now the question is, does this subset W form or is a subspace of M22? We saw before that M22 is a vector space. So the question is W a subspace or not? Unfortunately, you can read the answer there. So I should have put a box there. But anyway, so let's take a look why. Why this is indeed a subspace. You need to check, in principle, the 10 properties. I will show you in a minute that you don't need to go with the 10. You just need to be sure of the closure, addition on this characterization. But in principle, you will need to prove the 10 properties. But let's start by the first one. What happens when I sum 2 guys that are on this, on W? Here, A, B, C, D, and E are any real number, doesn't matter, generic real number, right? What happens when I add these 2 matrices? Well, the answer is A plus C, B plus D, A plus C. Oh, A, B, C, then let me write D theta. Oh, wait, then. So, A plus D, B plus E, C plus F. That's a number, what are those real numbers? You see, I'm summing 2 real numbers. That's a real number. So that's all okay so far. And now comes the moment, the crucial moment. What happened with this place here? If I do 0 plus 0, what do I get? 0, right? 0 plus 0 is 0. So this matrix here is in W. So W is closed under addition. Because if you sum 2 elements that are in W, you get an element that is in W. And if you do a multiplication by a scalar, of course, it is also. Why? Because any number multiplied by 0 will be 0, right? So the property 6, this was property 1, right? In the definition of vector spaces, right? And this is property 6. It says that if I have a number G and I multiply by one of these ones, you need to be close. What it means to be close? It means that the result must be in down. It obviously is in M22. That's not the question. The question is, are you in down? And, well, G times A is a real number, G times B is a real number, G times C is a real number. What is G times 0? Big, fat, circle, 0. And so, this. So that's why, in blue, hence W is the subspace of M22. The other operations don't really matter. Will it happen, for example, let's go back to this sum here. Will be the same design like this or like that? Commuting. Yes. It was true for every single matrix in M22, and these two fellas are two matrices of M22. So obviously commutative will hold, already associativity will hold, always a mean summation of 0 will hold, and so on. So these are really the two properties that are key. The closure against under addition and under multiplication by square. And that will be a theorem in a minute. But before I go there, let me do a change. Let's suppose that here now I define a vector space U formed by the matrices A, B, C1. Where A, B, C are real numbers. Question. Is this a subspace of M22? Answer? Answer? Say. No, it's not. No. And why is no? Because consider two matrices here. Consider two matrices here. And that one thing I will tell you later today if I have time, I probably will, is that when you're proving that something is negative, that is not a subspace, it is enough to give you a numeric example. You don't need to prove anything. When you're proving that it's a subspace, I need to use letters, you see? Because if I put 1, 2, 3, I'm only doing it for 1, 2, 3. But if I put ABC and tell you any real number, I'm doing it for any real number. But now we prove that it's not. And for that, I can put an example numeric. 0, 0, 0, 1. 0, 0, 0, 1. I don't care. I don't even care what are the other guys. Because what matters to me is that when I sum these two fellas, what will happen down here? 1 plus 1 is the old 2. And the important thing that is 2 is that it is not 1. So the result is not here. This is not, this set U is not closed under addition. Because I just got two fellas, very fellas, that are there, no doubt. They have ones on the right hand side, both of them. But the sum was not. Moreover, actually, it also fails the multiplication by part, right? Because 10 times 0, 0, 0, 1 is 0, 0, 0, 10. So multiplication by scalar also fails. You need to be for any scalar. I can pick any scalar. I can pick 10 or any number different from 1. Okay. So that's the basic idea. There are these shortcuts that I was saying. The shortcut is the following. If you need to prove that something is a subspace, you do not need to prove the 10 properties. Because the other 8 are hereditary, they are just following immediately. But these two need to be verified. And that's saying the following. If you have S is a non-empty subset of a vector space, then S is a subspace if and only if When you get two vectors in S, the sum is in S. And when you multiply a scalar, a real number, by a vector in S, you get a result that is in S. If you do, you are a subspace. If you don't, you are not a subspace. And this also shows you the strategy. The strategy is, if you want to prove something is a subspace, you need to use generic letters. But if you are proving that something is not, you just need to show a number. Yeah? That's enough. Because in the moment that you fail one mathematics, and you know a property, I'm talking about him, the student, a property, right? If it fails, the property is not true. And you must be true always to be true as a property. And here this property failed, right? Because 1 plus 1 but not 1. Okay. So this is I still have like 5 minutes. I would like to go to a point where I go back to this notion because I think it's very important. I will come back next week on this one that if I want to prove something, if I want to disprove something, or if I want to prove something, the different strategies. But before I go there, one more thing. This is also a nice way of checking if something fails to be a subspace. Consider S is a subspace. And take Z, the scalar Z. You can take any scalar, right? So take a scalar Z. What happens when you multiply 0 times a vector? Give you the 0 vector. But subspaces must be closed under scalar multiplication. So that means that C times 0 need to be in S. That means that the 0 vector needs to be in S. If you can show that the 0 vector is not in S, you take a look at the B, right? Like actually this one, right? What is it here? This one. Who's the 0 vector here? Who's the 0 vector? Who is it? It's a 0 matrix 2 by 2. The 0 vector is 0, 0, 0, 0. But guess what? I have a 1 here. I don't have a 0. So the 0 vector is not here. I'm saying that here for this view, the 0 vector, that is to say 0, 0, 0, that is the 0 vector, right? Is not in U. It must be. Because if it is a subspace, it needs to be closed under scalar multiplication. So 0 times any vector you want, give you 0, the 0 vector must be in the set for a set to be subspace. Of course, you may have the 0 vector and not be a subspace. But if you do not have the 0 vector, you are not a subspace. So that this type of property helps you very quickly to show that something is not. It doesn't show you that it's a subspace, right? If the 0 vector is there, it's not a proof. It's just that, okay, we need to continue working. But if the 0 vector is not, it's not possible. It's not possible. There are these two extreme cases. The extreme cases of subspaces are the whole space B, because in sets S containing B, S could be B. In other words, any set D is contained in B. So the subspace entire vector B is a subspace. It's a trivial subspace because I didn't do anything. I just keep the original vector space. But it is a subspace. The other extreme is not the empty set. It's not the empty set. It is the set that contains the vector 0. Why? Let's go back to the definition. And then take a look at that property 4. What property 4 says? There exists a 0 vector in B. There exists a 0 vector in B. That means that there must be one vector in B at least. You cannot have a subspace with no vector whatsoever, because at least one vector must exist. And that is 0. So you can have just a 0 vector, or you can have the entire space. Those are subspaces, yes. Are they important? Not really, they are trivial. The important ones are the middle ones. And to finish, I want to say something about this. How do you prove or disprove subspaces? I will come back to this because this is a very important notion for your exercise, right? When you want to prove that something is a space or subspace. So here are the two issues. If you need to show that something is not a subspace, you do not need to prove. You just need to give one example. Like I did right there. I picked the 0, 0, 0, 1, 0, 0, 0, 1. It was a 2 there, done, out. So, to show that a set is not a subspace, provide two concrete vectors, like I did there, two matrices you see there. Concrete vectors whose addition is not in S, or the multiplication by a scalar is not in X. And that is enough to prove that that set is not a subspace. Also, for what I said before, if you don't have the zero, it's also, you are not a subspace. Those are quick ways out. But if you need to prove that something is a subspace, then you need to do it like here. You need to prove that if you sum two ℘, you get a ℘ in the set, and if you multiply by a scalar, a generic element here on your set is in the place. So that's part B of 7. To prove that a set is a subspace, we show that the sum of two generic vectors of S is in S, and we show that the multiplication of a generic vector is in S. And if that happens, then yes, you are sorry. So I would say that, okay, you have a test today, right? But I mean, after the test, you may want to go back and recheck this for next class, because these are really important concepts for what will happen for a few weeks now in the future. Okay. Any questions? No, back today and see you on Tuesday.
Like I got it, but like I don't get how we would do examples.
Oh yeah, he didn't do a single like actual example.
Like, it was mostly just theory, so I don't really understand how we're gonna apply this. Are you going down?
No, I'm waiting for you guys to go. Hello. Do you have anything now? Do you have anything now? Yeah, me neither. I got one already.
Go study right away, probably.
Yeah, same.
Yeah, my friend, I think I'm gonna be my friend, and then I wish you luck all the best. Let me know how it goes, okay?
Wait,
You guys have Discrete? Where's Krisha? She didn't come today.
she's studying for the test.
Valid.
I don't know why I came to class.
Yeah, same. I feel like I shouldn't have come either. I wasn't listening that much. Oh my god, hi! I haven't seen you since last semester. How's life?
Notifications turned off.
Oh, I see now.
Yeah, I'm blind. What about yours?
Same. I'm behind.
Okay. I feel like I'm always sacrificing a class.
Yeah. Are we all ready for the test?
I think so.
Hopefully. Question mark. I'm studying a little bit in class. I don't know how much I'm like.
I looked over the slides for the determinants.
Hope I don't mess up the rules. There's a lot that are similar.
Yeah.
Like
It's
the
like so
determinant
easy to
one.
make a small mistake that like
I know.
ruins
know.
everything.
Oh my god,
It
yes.
pisses me off. When I add a number instead of subtracting,
know.
one row in the matrix.
No,
and
I was
everything
thinking I'm
else
gonna
is-
take a scrap paper and write every single thing. Not do it in my head. Like 1 minus 2.
Yeah.
I'll come with you. Bye. Bye. Library?
Maybe.
Okay.
I think I'm gonna go see my dad first, though.
Do you want to say hi to my live viewers?
Oh, sure.
Hi. Hello. My name is 𝓐𝓫𝓸𝓾𝓽. Hello, 𝓐𝓫𝓸𝓾𝓽. Sidang yan na live view. Yeah, I do live streams. I'm so hungry. Ang maganda. Lankan, 2:30 a.m. And they're still at work. Hadi, bye. One of them is going to say
When you actually get really through all this algebra, you can literally get anything done.
Do you have anything after, like before the test? Do you? No.
We didn't do an exam.
We should have went the other way.
It's like everybody's wearing this test. Is that our teacher, our professor from last?
Oh my god! You're right. Our calc professor.
That's the first time I've seen any one of the teachers there, yeah.
Yeah, that's true. Like anyone I recognize. Library යන්න කලින් canteen එක පැත්තේ යන්න ඕනේ නැත්te. ඔව් මේ lunch එකක් ගෙනා. ඒක කන්න. ඒ නිසා oh my god. ඒකයි 100 පාරක් Philippine. Hello. You need to book those. I never booked them.
I would have literally imagined if one of us were
We went a full circle for nothing.
Trust me, you're not gonna hurt. You're gonna start coming to every class.
Where are we gonna sit?
You're not even fast.
Oh, yeah. Okay.
Do you usually come to the library study?
I sit here if I have like a gap. Do you? Only if I have a gap because I have nowhere else to go. We could take that table with the TV. Do you want it? This one? Yeah. A chair. Wait, I'll put my bag so that we have a seat here.
Wait, I think I see one.
Okay. My name is 𝓐𝓫𝓸𝓾𝓽. Oh, ඒක නිකන් ඒගොල්ලන්ට විතර ඒකට යන්න පුළුවන්. Even look at TV screen at the end. This is my first time using one of these. Really? Okay, I'll move this way. studying for the test?
Oh, going through the textbook questions.
Yes.
How about you? I think I'm just gonna go through everything again.
Yeah. Do you know how long we get this test? A whole hour?
I hope so.
Okay, but there's only like what, 7 questions?
Really?
Oh yeah, like 5 multiple choice and 2 long ones.
Yeah.
And an hour for that?
Maybe the multiple choice take a while though.
Yeah, I'm scared for the multiple choice. That's a lot of marks for.
Well,
And
for what?
Yes. And there's 5 options. Only one's right. So yeah.
And no part mark.
Oh my god. Oh, multiple choice questions. Pahai. Short, long answers. They got. Kata mo yun? Oh yeah, the Olympics started.
Oh, really? Oh, the winter one?
Yeah. Is nothing working? Yeah, mine's working. I don't think it works. You can't download it at school, but I have the textbook downloaded, so we can share it. What question? Rather than like 5 choices, like we select then after multiple answer questions, then will be a mark group. Oh my god, negative marks?
Negative marks?
Yeah. I get marks taken off.
Oh.
Are you at them? Which ones have you done?
I don't know the specific
Okay,
numbers.
just random then?
Random.
Who's the... What is this? Have you done like the sample thingies? Or they got sample exercise?
The sample exercise?
Yeah, right here, these ones.
Oh, no.
Okay, we can do those. I did do them though. I said that.
went over the tutorial, all the tutorial stuff.
Oh, like what you did in terms with the team.
I couldn't find the specific pages for the questions. So
I wish we had like the assignments we had for Carleton.
yeah.
That'd be good practice.
Or the weekly quizzes.
Yes, either. I think I like the online ones better though.
Yeah.
Because unlimited try. Convert the matrix to REF. R. Do you remember all the rules?
I remember like the vague ideas.
Yes, I
Not the names or anything. Oh my gosh, I think this is the
No, oh wait, they can't see you. May sing Haryali. Hello.
The bottom one, that was 0, right?
0?
First one?
What do you mean? Wait, what was your question?
But there was a 0, right? 2 was 6.
Oh yeah. Wait, yeah. I forgot about that. I was even thinking of it. Wait, and then you could just do R3 minus R2, right? To get it to look 0?
Yeah.
1, they're asking for Sophia because she's been on my life. That's it, right? That's the answer. The R. That's what I got.
Wait, I did one more step to make the top one.
0?
Yeah.
Yeah, maybe I do that.
Because it's R, yeah.
Yeah. So 1, 0, 1, 1.
And then 0, 1, -2, 3.
Like fill it up at the deli place. Yeah, alright.
You have to write that down.
Oh, why is this a 0? And this. Lagi habang tinakabot yun na nida. Rapod yun.
Podkiona.
Yeah. Wait, this is the only thing that's different. Yeah, it's probably. Yeah, I feel like it is. Checking wallpaper exactly. What checking? ඒක මාරු වෙනවා. දැන් අනේ කොහෙන්ද පොටුසේ? මේක නේ. අතහැරුවොත් තායි කියනවා. අයියෝ ගියා. අපි මුවී තීටකට ගිහින් බලුවා ඒක ඇත්තටම මාර ලස්සන නෑ මේ මගේ left hand එක.
You're the one who was waiting for me.
වමනේ අපි දෙන්න watch එක සාමාන්‍යයෙන් දාන left hand එකට ඒ දක්වන්න නෑ මම left hand එකට දාන්නේ
You touch my collar.
question. For these, oh wait, this we don't have to do this. Do we? This system has infinitely many solutions.
Wait.
Right? Because it's asking what type of system it is.
Oh, I thought it wanted us to
Yeah,
make that
I know.
system.
I was like, we don't have H and K.
I was so confused.
Yeah, it's C. Yeah. It is C, right? Infinitely many solutions are 2.
But is it 3 free variables or 4?
Is it 2 free variables?
Wait, hold on. Oh yeah, 3 free variables.
Yeah.
Wait,
2. Because this doesn't count. This is like the B. What question? No, it says it's B. Huh? There's definitely a solution. wait. I'm gonna ask Jenny or something. The first one was wrong too. So either we're wrong or the textbook. There's like this 1 year free trial or whatever, so I think. Yeah, correct answer C, infinitely with many solutions. So we're right.
this is a really bad textbook.
No, I'm gonna check the first one too. I'm bored.
I forgot how to make free variables.
Is that one? 0, 1, 1, 0, 1, yeah, okay. Wow, what an awful textbook. Okay, number 3.
The second is
Which one's no?
No solutions?
Yes. Because the second and the third reason, the left side looks almost the same except flip, but then the right side's different. The second and the third.
This one, yeah. 99% of the correct answer when decomposed. मैं कि हमें नहीं मेरे मैथ में को मैं कर Yeah, no solution because 0, 0, 0, 7. You don't have to do the top round. I'm not even gonna do it. Something.
No solution.
No solution.
If that one says it is a solution.
So C is okay. That one's right. Okay. Yeah. physics, chemistry, Italian, CP में कानू है नहीं
What if the system's inconsistent?
Huh? It means there's no solution. It's when this happens. For no solution, I did h equals minus 2. K does not equal infinitely. They both equal that number. H equals minus 2. Unique is h does not equal. And K Answers 8. Why is it D over 7? Huh? Over 7. I know. Are we doing question 5? We are doing question 5, right? 4. No, 4. Okay. Oh wait, I totally forgot. I was doing like both of them together. Anyways. D equals yeah.
I thought you were just doing extra. I was like, oh, actually, that's hard.
No, I started to look at this, and then I thought that was the question. Okay. So D, that's right. 5.
Oh, bro, there's a lot of food.
Oh, when did my brush change?
I think
What attitude do I have?
Yeah, we do. I mean, we don't really need we don't get programming.
That's not algebra.
Yeah, that's I've never heard of that too. That's cool. Is it easy?
Oh, why didn't you do it in a row?
That's confidence. Yeah, physics is not that easy. Did you want to yeah, even like just at least it's good. The scheming is good. I don't think you need to feel the final. Oh,
I wonder why.
huh?
He told you that one. Yeah, I know it's the
I messed up there in the third one.
And I have a 1 point.
Where's your master?
They're huge.
Everything is everything.
What about? Why not this way? We can also check.
K is 0.
K is what?
K is 0. Oh, wait, K is not over 7?
Yeah.
Yeah. Okay. And then infinity would be H is 3 over 7, K is 8 over 7. Infinity would be H is 3 over 7, K is 8 over 7. I'm totally ready.
We've been doing well.
Great.
But this is still like the basics. We can do like the inverse transfer stuff.
I might go for this. I'll be back in like 20. It was just a while, yeah.
It's his first time teaching.
See you soon. Done with video size.
Bro, what the? If you fail circuit, somebody fails circuit. You need help for that. Thank you. You guys are weird. Not at all. That's why I was sitting. I was like,
Just David. Right, I've seen red spellers.
Sorry. Can I get the chair?
අමතක නෑ දිනුරියා යනවා කියලා Tamam. Tapos.
Çalışacağım mı? Nasıl gideceğim? Sen değil mi ama?
Tamam ben bir de saçımı da ona benim kodum söylüyorum.
Ben o değil mi? Sen
Dedim güzel. Onda bu kadar işte 5-7 arası 7'den de ona kadar.
Ben sana mı dedim?
20 saatte geldik biz. Yemek yerken dikkatimiz dağılıyor.
Yemek bir şey söyleyeyim mi? O saatlerde efsaneydi ya. Kemal'e gidiyordu. Anlıyor musun? ChatGPT yazılmış abi. ChatGPT yazılmış. ChatGPT yazılmış. Sadece yazmak size gidiyorsun. Sen geçsin. Gerizekalı
Kadın şey yapmak istiyor. Bütün stekleri
Ya bunlar front COD. COD.
Do you want me to send you some student training
şey söylüyor. Bakıyoruz biz hoca geçen dönem.
Ben size format yaşalamayla aldım. Beni yer almışlığı alsam geçti.
Tanıdın diyor. Bir de almış.
Hayır. Zaten çalışanlar var şu an.
Senin kötü aldın. Ben dersen kalma. O iki almasın.
Şey market. Bütün
Kalsın. Allah'ın
sana çıkıp postane esasında
Vereceğim var ya. Adam bir şey görmüyor. Üniversite öğrenci gibi. Adam bir
biz tuvalette birbirimizi yermek. Oğlum bir yere telefon sakladım.
ben telefon arada notları şeyin arasına sokuyorum.
Tuvaletin şey.
Tuvaletteki şey var ya. İşte çekmeyelim dışarıdaki. Onun arasına şey sokuyorum. Ya. Gelip çıkarıp bakıyorsun.
Saat olmuş.
Ben bazen ekstra şey yapıyorum. Hiç bir anlaşmadım ama tanıdığım birini görünce telefonla da beni. Küçük bir telefonu aldım 90 aldım.
Yeah. Like I was just like last semester I was on
Herkes emin olduğu soru cevabını kağıdın sonrakine veriyor. Ben çok zor. Ben çok test Oğlum sana çok benziyordu. Bir de ben sıkı kaçamadım. Tamam. Şeyde kaçamadım. Ders yapıyordum. Ben o
Kim şu? Geçen 74 demiş.
yaşlı.
Why are they so I'll point at them. Literally, I'll point at them. Oh, there's that cheese. Maybe it'll be in the top crazy.
Okulun bundan okulda hiç gerek yok. Bak yeni kanalda var. Bir şey diyeceğim. Şu güzel açar mısın?
Mahsus yapmam lazım. Bir dakika öyle yazdım.
Bir gezelim misin?
Olmuyor işte. Zaman yapalım.
Yok böyle hocanın gözü benziyor. Hoca notları sadece o kıza atıyor, kız da sadece ulaş atıyor. Valla şu an hatırlarsın notları edemezsin. Ama hazır tutuyor.
Adam kadın ama alabaş gibi.
Alamayız. Kadar yeni soruyla gitsin. Saçma şey. Benim tabureyi paylaşırız.
Daha şey alalım. Bir tabure vardı ya geçen. Kaybolur lan. Bir de şifremi yok bir şey.
You actually scared me. I forgot where we sat and I was wondering where that sat for a while.
Like simple math mistakes. Which was number 6. Number 6. It's so long. But I finally got it. I asked
Bize sunum yapıyorlar. Senin de
But they said hi, welcome to the room. Hi. Yes, fine. You know what? Giving us an hour is understandable. I'm gonna go so slow with the math. I keep messing up.
It'd be really sad if they didn't do this
Yes, Lanka.
O da boş boş.
Oh yeah, sorry. There's a question. The question. You were asking which one I was doing.
Oh yeah, that one. I saw it.
Oh, okay, good. I thought you'd have enough time to write it down. We have less than an hour.
Çekilmez artık bize gerçekten gibi odanın numarası gibi. Kodu bulmaya çalıştık. Alabaşı'da kesin. Yalnız o da ciddi bakıyor.
I'm trying to my math, so I'm sure like
I know. Here in the name, Mommy. Did you eat lunch, by the way? Okay. No, I'm eating right now.
Orada da aynı ortalıktan değil. Hayır, daha fazla bahsediyorum. Şu an verirsen, bunun için geldi. Genel mantığından bahsediyorum. Ne kadar iyi bir şey zaten doymuyor. Yıllar nasıl?
Ya ben şimdi ekmek ben pizza karadarayak ve
Nerede yazıyor? Nerede yazıyor?
Narakaya Mariana man pizza
Ben
karadarayak.
yardım edeyim.
Oh, bir de nasıl yemiş?
Kayıtla sokuyor. Okuma gerek var mı? Orada aklına nereye tutulmuyor.
5,5 söylemiştik ya. Benim şu orada olalım. Bir şey zaten. Yani bizim de öyleyiz. Biz zaten 20 yılda öğrendik. Neden biz de öğrendik? Her gün 20 gün, her gün 20 öğreneceğiz.
Her gün ama değil.
Her gün 20 öğrendik. Bu hafta 3 kez 20 öğrendik. 3 kez mi? Önceki hafta değil mi? Ondan. Tamam. 20, 10.
Abi sen ne diye böyle bir fotoğraf var?
Ya bilmiyorum, benim elimizde yemek olacak. Ben her türlü yemek zorundayım.
Daha önemli. Nasıl yapalım?
Evde yemek.
Ben mi yedim? Sri Lanka ve birthday vlog ka birthday plans ne?
Orayı da ben geri gel. Buraya geri gel. Ondan sonra geri gel.
Kaç tane ne yapıyor?
Ben de işte eve gidip çalışıyorum.
Parang kas ko rin.
Ya yemeğe boş ver, başka yemek.
Ako gawin ko kanda. How to taking everything.
Bu adam ediyorsa ben otobüse gitmekten daha iyi ki 9'da otobüs hiç çekemem. Ben ben seni çıkayım. Ben sana onun görgüsünden ne var? Hayır. Görgüsü sen ne diyorsun? Hayır, görgüsü sen ne diyorsun? Hayır, görgüsü sen ne diyorsun? Hayır, görgüsü sen
May floor के साथ में कर लगेगा. Silent floor के ना first negative. के साथ में करना. लेकिन इनका group कोड़ा.
Abi nereye gidiyorsun? Tünellerden gidelim. Abi kaç dakika gidiyor? Tünellerden...
İsmail, girdiğiniz binaya geri döneceğiz. Ya madem 2 dakika oturup gel. Amına kodumuz sala. Sana ben ne dedim orada bekleyelim diye.
study areas තමයි තියෙන්නේ. library පොත් තියෙනවා first floor එකේ. ඒකේ move වෙන bookshelves තියෙනවා. And then තුන්වෙනි තට්ටුවේද පොත් තියෙනවා.
I don't know. I would look for like it.
Is the answer x1 is 0, x2 is 1, x3 is 0, and x4 is 2?
Yeah, but then since it's a free variable, don't we have to do like the TP?
Wait, what's the t?
So then, like, you say let x4 be 2, and then you plug it into the equation.
Right.
So the solution's infinite. Yes. Then I must do 7. I got no solution. These ones are long. After that, I can't remember that. Maybe bilingual, French and English දෙකම ලස්සනට පාද බැලුවා. ඒක ලස්සනයි. ධර්මයුද්ධය ළඟදී බලලා ඒකත් හොඳයි. ඒක පාද එක තරක් ගත්තා. මම බල හිටියේ මොකක්ද අර පරණ එක. ලියනාඩෝ ඩිකාප්‍රියෝගේ මොකක්ද Catch Me If You Can ඒක ඉවර කරේ නෑ හැබැයි. නිසා කවුද හොර?
Wait, how do you write
You do like the coefficient and then you do the t.
the coefficients are on the right side, this thing, right? Wait. This is a coefficient?
No, like, okay, wait, so you say, you get the final matrix, and then you say, let the free variable be t or something, and then you start plugging it into, like, the shortest one, so then I put it in here, and then instead of x2 I put t, and then I get x3 equals t, and then you do it for the next one, and then you do it for the next one. නෑ නේද? මේ දවසට එක කවද මට? I'm still on 7. Yeah, because I made a mistake.
What are some of the harder ones? Just like skip them.
Sure. I don't know which ones are harder. I struggled on these two.
I mean, like the determinant ones.
Oh, yeah,
Like,
you're
get
right,
some
you're right.
concepts
You're
down.
right.
So many
What
squares.
even are these? Economic models.
This is community and arts too.
Top.
Like the name's pronounced Leonard, I think. Is it Leonard? It's not Leonard. I think it's like Leonard or something.
Yeah, I think so. I had a teacher named Mr. Leonard.
I think it's something like Angry Birds or something.
Okay, we have these things. I did do these last week though. Yeah, we could do them again.
Sure.
Can deeper than name your expression. T is transpose, where it's like the rows become the columns. Inverse is like the identity. You know, where you have like A, and then you start making this into an identity. I did this last week, but I already forget. It was hard.
I smell like fresh crab.
Oh yeah, I forgot about that. You're right. Yeah, thank you. But I still don't understand how. Oh, see. Yeah. So that one's cancelled. The A was cancelled, and then B gets one. Wait, so when you do it, if you were to show your work, you do A to the -1 to the -1. Yeah. Or wait, you start with C, because it's like backward. So then C to the T to the -1 to the -1 times C to the -1 times Hello. My phone's about to die. I forgot about my phone's battery. Everything's about to die. iPad's at 22. MacBook's at 44. 44 is okay. 44 is okay. I don't need a calculator. I didn't bring a calculator. But it's okay. Yeah, I don't think. Should I bring a pencil?
Wait, are you going to just like do algebra so you can divide like a whole thing by another whole thing?
It'd be the inverse, right? Dividing. You'd be multiplying by the inverse. Hey, I remember when when I did this last night, like I got 2 minus 8, right? So then it's negative. Then I'm pretty sure in the answer there's like positive 2 for that.
Yeah, but technically you could do 2 minus each one, so you do 2 minus 1 is equal to 1, 2 minus 2 equals 0, 2 minus 0 is 2 minus 2. But then you have to do it before the inverse. Wait.
Wait, why is my math wrong? Oh wait, no, I mean like 0 minus 2. That's minus 2, right?
But you're not doing 0 minus 2, because if you wrote this another way, it'd be negative a plus 2. So you'd make it 0 plus 2, or like negative 0 plus 2.
Yeah, that's what I mean. Like, how do you know what's the word? Like, how did you figure out the word? Like, if, why is it not? What did I make? Yeah, minus 2 minus A.
Yeah, 2 minus a, but it's not the same as a minus 2.
Yeah.
You did a minus 2.
I have 2 with it. 0 minus 2.
0 is from a though. Well, 1, 2 is something you're minusing, right?
Isn't 0? No, because like 2 is the identity matrix, right? It's like 2 hash. So that's 2, 0, 0, 2.
Really?
Yeah. How did you do it?
I just subtracted 2 from everything. I don't know. Because when you like to like subtract stuff.
Is that how you're supposed to do it?
I'm not sure.
Huh. We should search that up. Hello. Oh wow, I think the collection. Yeah.
It's fun. We still have half an hour.
Yeah. Okay, wait, I'll just put the whole question. What is it? Sorry. How do I do 2 minus 8? Yeah, okay, so it is negative. Sorry, I just did. Imagine this is wrong. It better be right. Hari, bye. Bosan na. Mangin ka na dad.
I said one.
this is also a problem. How did they... Why is the x behind? How do you know to keep the x behind? Like when you usually factor something, you put the factor thing behind. But like the order matters in matrices.
Right. I guess would it be because you didn't write x2 and xa was 2x ax. So since it comes after there, maybe you put it after?
Oh, you're right. Yes. That is an important observation.
I don't know, hard to like
So now it's
notice.
Okay, now to find the inverse, we need to see if it has. So then it's -2 minus 2 Oh, I'm Uni Student. And then multiply matrices. -2 times 1 plus 2 times 1.
Oh, she is.
Mangkarane computer science degree ka dan karane math test pada. 2 plus 2 0 plus 1 2 plus 4 plus 2 0 1 6 I messed up. Did you get it? Yeah, 0 6 1 1.
I got
Yeah, also
negative a half.
okay. Also, where did we mess up? Okay, now that we got that.
What did you do when you... Wait, what did you get for
Oh,
I
that
plus B?
determines 2. I got negative 2. That's why it's wrong. No, wait, that's still the section. Yeah, like when you find the inverse, you put the AB 1 over AB minus AC. Oh, it's still wrong.
Wait, so for the inverse, did you do like before the half when you put in front 1 1 0 a half?
Oh, that's not how I found the inverse. Since it's a 2 by 2, what I did was, you know how it's A, B, C, D? I just did D, A, negative B, negative C, but then times 1 over the determinant. Yeah. But it's still wrong. Where's my...
Sir John
Four, 2, 1. Oh my god, so many small math mistakes. And driving jump is a bit in the plan. Hitang neva kiva tina. Didiri na Uber tina. 1/2, 4, 2, 1, 2.
The final one?
Yes.
Take the half out of everything?
Yeah.
Okay.
And then, oh yeah, good luck. May masinin. Oh, masih yes, degree.
These two are parallel, right? What's that? Here.
Do you feel confident? My confidence has the whole word, so
My confidence, like,
yeah.
it's the other side of the world.
Yeah,
It's
so
like
many
that.
things. I keep forgetting. I did do this yesterday.
So many tiny things.
I wish we could bring a cheat sheet that everybody uses. What was that? I just wrote a bunch of it. Yeah. I know I'm gonna mess up. It's sad.
What's the third column? That's all the questions there.
I'm gonna do the whole thing and then figure it out. Like, I don't remember the tricks and stuff.
I keep forgetting the tiny stuff. Like,
Determinant, if there's a determinant, the scalars with the A, K to the N. I'm gonna forget that.
It's coming from here, so here there's zero.
Oh yeah, do you understand this stuff? I don't have any fashion questions. You know how, like, when you do something to, like, in the process of doing this, right, and then you do like that step to just the identity, and you get this? Yeah, same. It's okay.
I should post both of those in the test.
We should, yeah. How about we have them next week? And yes, the TA questions today.
How much is the way to
Oh, wait, let me check. That's very high.
It's a big number.
Yeah. Oh, yeah.
This is the most bright you have ever seen.
Closely it gets easier from here though. Or some people say the harder stuff in the start. One person told me that some
people had it.
So like people would take it like before.
Oh, last semester. Yeah, hopefully he's like our class professor and has easy questions.
Factor expansions and you take out over one column. And multiply them together. It's like,
What did you say?
cofactor expansion.
Oh yeah, what was that?
It's where you take out one of the rows of the column.
Oh yeah.
Take the things that you take.
Oh yeah, I remember this. I just didn't know its name.
I'm not going to remember its name. It's like, use cofactor expansion.
What was that again?
You do this to find the determinant.
Right, yeah.
And you can like, if you get a big red thing, you can do it again.
The shortcut.
Yeah, and then you have a third. Oh, for the determinant, all you have to do is the line thing.
Oh yeah, and the upper triangle thing. And the bottom triangle. Multiply the dash.
Where one side, everything on the right side is plus and everything on the left side is minus.
Yeah, I need to remember the order. It's like this, and then you start here and then you go backwards. I've been messing up. One time I did this first, and then that, and then another time I did this, and then it went backwards. Yeah, I remember. It's a lot.
How much I spend in 3 days?
Good question. Oh, marune.
Right. And when you first determine a negative or like a b to a negative one or something, that's 1 over the determinant of the negative.
Yeah. And reverse would be 1 over.
Yeah.
And transpose is the same, right? Is it always the same? Or is it? I saw something where it was like. Oh no, that's A plus A plus B. There's the natural. Right? Yeah.
Yes.
But the determinant's always
Don't get out.
I think this might be the only thing I'm wrong with.
I don't regret it.
considered.
Because you can like.
We don't have a lot of time.
We don't. So, you know what? We're gonna pass this. We're gonna record ourselves the next one.
Yeah. Definitely. I don't know. I don't have hope for the next one anymore because I haven't been listening. I keep zoning out.
I'm gonna start. We're gonna start walking.
You know what?
We're gonna start walking.
Yes.
It's just necessarily to make sure you stay on top of it. We should start doing competitions. It's the homework. Like stutter service
So
homework.
we have like a streak.
Yeah, like every day or like every week or something.
Yeah.
If
It's
you
a challenge.
do it
And if
that
you
day-
don't do it, you lose your streak.
Exactly. And you have to restart.
Yeah.
Every day you do like,
It's like, you know how like we used to do prodigy in school?
yeah.
And then it's like the leaderboard.
We'll just keep a running leaderboard in Discord. It's like pin 2 messages with each of our points and we'll edit it.
Yes. But we don't have homework, that's the problem yet.
We find homework in the text and then do like 3 questions or something.
I love that like thingy that the calc teacher had where it was like, yeah, just that was so nice. And easy marks. I wish we had that.
We don't have it now though.
It's okay.
We bought this.
Yes, good luck.
Good luck to you too.
Where's your part?
Seven.
Oh,
Where's
I'm
yours?
in the day. Very close.
Tough. We might want this one, but we've got the next ones.
At least an 80? 80?
At this point, I'm just hoping to pass.
I don't know, yeah, an 80 seems kind of unreasonable too. Which, so each MCQ is, yeah. And then how much are the long ones?
10 points.
That's hard. Why can't we have more long ones?
I'm just
That's
gonna
more part marks. I like having long ones.
yeah, because there's part marks.
Oh, I'm gonna have so
All the sides
small
while we're working.
math errors. Mess up my
forget
whole
what things are
matrix.
I'm gonna forget what things are called.
අක්කා කැනඩා එන්න ඔලිවර් රිසර්ච් එක බලන්න. මම හිතන්නේ O level බලන්න A level බලන්න ඇති.
Do I? I hope you don't get it.
Sometimes it just freezes after. It's a
Bye, Dishaka.